Considering the effects of climate change on our society, more and more industries are setting up zero carbon targets for the coming years. Since the major source of emissions relates to energy consumption, renewable energies and hydrogen are key solutions to overcoming this challenge. But what if industries improve their energy efficiency first? In particular, what if they recovered and valorized excess heat instead of letting it go to waste? By 2030, about half of all global energy will be released as waste heat. If the heat of the off-gases of European plants could be recovered and converted into electricity, this would be sufficient to meet the electricity demand of Berlin, or even meet the demand of Luxembourg twice over. But how should the energy be recovered? At what temperature and mass level? And once it's been recovered, how can we best valorize it? And this is where ValueHeat comes in. Our platform collects the different tools that we've developed on the topic on waste heat valorization at the Luxembourg Institute of Science and Technology. By providing process engineers and energy auditors with ready-to-use calculation and optimization tools, ValueHeat not only supports them in their day-to-day assessments, but also unlocks the untapped waste heat potential of industries. Two solutions are currently available: Quick Pinch and Heat to Power. Quick Pinch is an easy-to-use, free solution for managers and engineers looking to estimate their waste heat potential. It provides quantified data regarding steam and electricity production, as well as heat supply to 3 different types of district heating systems. Heat to Power, on the other hand, is an optimization software focused on electricity and steam production from waste heat, and is specifically designed for process engineers and energy auditors. Are you wondering if waste heat valorization is a topic for your company? Or are you already working on this topic and want to save time while generating optimal solutions? Then ValueHeat is definitely the place to start. Good morning, everyone. My name is Alex Bertrand. I'm a researcher at the Luxembourg Institute of Science and Technology. My field is waste heat valorization, and this is the topic, of course, that we're going to address today. Before we start with the presentation, a short notice, and this webinar is going to be recorded, so it will be made available online afterwards. And also, if you have any comments or questions, don't hesitate to put that in the chat, and we'll answer these points after the presentation during the Q&A session. So, what are we going to talk about now? Well, we're going to talk about waste heat valorization. Is it really a topic? Is it really relevant? How much waste heat is available, and how should it be used in general? We'll then move on the actual technologies, on how to recover them and how to use them. And we're going to focus on one side on fluids, meaning gaseous and liquid streams, as well as addressing solid stream waste heat valorization. In the next step, we're going to talk about related challenges. So it's mostly about optimal design of waste heat valorization, and then also a crucial point, it's operation, mostly fouling problems which are limiting waste heat recovery. We will then move on to the conclusion, and then again, after the conclusion, we will move on to your comments and questions. So why are we talking about waste heat valorization? Why is it even relevant? Well, if you look at the broader scope of one of the major challenges of our society, which is climate change, when we see the main source of greenhouse gas emissions are related to our energy consumption. And the issue is that basically when we are looking at our energy consumption, only about 40 to 50% are indeed being used, are being emitted as waste heat. These are really being lost through our environment. So that's why when we see this kind of value, we realize that basically our processes are not that efficient, and we should actually see to recover this lost energy. So what are the common waste heat sources? But we don't need to go and look very far. Actually, at home already, we have the showers, or simply our bath tube, where we are actually using hot water for a short time and then remitting it to the sewer. So that's a source of waste heat that we have already at home. Another source is our non-electric cars, for example, when you see the efficiency of the cars. Currently, it's about 30 to 40%. The rest is being heated as heat. We do use part of this heat to heat up the inside the car, but for the rest, it's being heat lost again to the environment. Another source is a ventilation system. So it's ventilation at home or in production halls or in data centers, where we basically need fresh air. And this fresh air is used to replace old air, old heated up air. And this hot air could actually also be recovered because it's also lost energy to the environment. Of course, the biggest block of waste heat is related to industrial production, industrial systems. So here it's mostly about the off gases, where we are burning fuels to produce heat to transform certain processes. But here, when we're considering the off gas temperatures that we have here and the quantities that are emitted, we are losing here a huge amount of energy. Another source is related to the production is the cooling of, for example, furnaces or production systems, where we need to control the temperature of the equipment to avoid its destruction. And with that, we're using cooling towers. But basically, it's just a transfer of this excess heat to the environment, and very often, again, lost to the environment. Another possibility is the solidification of liquids. For example, in a glass or in the steel industry, where we are forming certain kinds of materials, and once they've been poured, they can cool down to their actual form. But this cool down process, again, it's lost waste heat. So waste heat valorization basically is not just about quantity, but it's also about quality. And this is really a very crucial aspect. I've had already many discussions about mostly data centers, where we see a huge amount of waste heat available. But the problem is, when we see this, when we see data centers, they come up with very low temperature waste heat. And the issue here is that basically we can't do much about it. So when we are thinking about waste heat, it's quantity and quality that are both equally important. When we look at the potential, there are no formal concrete values on waste heat potential. There are now more and more projects working on this, trying to quantify in a better way the waste heat potential that we have in the different sectors. Here you see a more recent study that was done for the European level, at European level, concerning the waste heat potential in the different industries. We see that the biggest share is between 100 and 200 degrees, but we see also that between 500 and 1,000 degrees was related to the, for example, glass industry and the steel industry. There's also a very important potential. Of course, what we don't see here is the potential from the data centers. I've been looking into it, didn't find recent values, because here indeed, with the increase of AI, with the increase of data management, this is going to be a topic, of course, but again, it's low quality waste heat, and it's difficult to really do something really sensible out of it. Why is the temperature level really that important? Well, it's simple. It's the higher the temperature, the more valorization opportunities we have to use this waste heat. So when we see how we could valorize the different sources, we can on one side do waste heat recovery for process preheating, for drying, so that's a direct waste heat valorization. We can also use this waste heat to produce electricity through standard turbines, through OSVs, or through thermoelectric generators. We can also use this waste heat to produce superheated steam. at a lower temperature level, we can produce saturated steam, we can produce chilled water or fresh water. We can actually also start producing hydrogen with that, although we have related electricity consumption related to that. Or for very low temperature applications, we can use this waste heat to inject in district heating systems. When we are talking again about data centers, in this case, we would need a heat pump to increase the temperature level. Unfortunately, this means that we are going to consume electricity again to reach good level of quality in terms of waste heat. So when we are looking at the actual values of this waste heat valorization, at European level, there was some estimations on what is available in terms of waste heat and how could it be valorized. So when we see, if we were to valorize the off gases, the industrial off gases in the EU, we could produce about 13 terawatt hour of electricity per year, and we could save about 4.4 megatons of CO2 emissions per year. And this is by doing waste heat to power solutions. We can, of course, replicate to reflection and see, okay, what would happen if we were to use this waste heat for district heating systems? Here, the biggest problem is that as opposed to electricity production, to do waste heat valorization to district heating, of course, you need a district heating system next to it. But it was very interesting. There was a European project who actually addressed this question, and they realized that actually for quite a large number of industrial sites, about half of them were within a distance of 10 kilometers. So there is some potential to connect and use this waste heat for district heating system nearby. So if this waste heat was indeed valorized and taking into account this geographical constraint, we could cover about 17% of the heating demand at European level. Another possibility is to do waste heat recovery at home, not only in the ventilation, but also on our gray water. So already mentioned before that, the shower, the bath tube, but also the laundry water or the washing machine. So we do have several sources of waste heat, and we've done several assessments. Of course, for, let's say, old buildings, that doesn't play a role, but this solution is going to become more and more important in the future, since our buildings are being more and more insulated, well insulated. The air losses that we have through better ventilation are reduced. Now the next challenge will be actually to recover the waste heat that we have in our gray water. And here we've done several scenarios. So we've seen that if we were only to concentrate on the shower waste heat recovery, we could save up to about 10% of the electricity demands required for the heating demand in a near zero building, in a near zero single family house. And this value could go up to almost 30% if you're really pushing it to the maximum. So that means waste heat recovery, but also decreasing the hot water temperature instead of 55 going down to 45 and so on and so on. So actually there's also quite a lot of things to do for our gray water, and one of these measures is to valorize the waste heat of the water. In terms of market potential, it was estimated that by 2030, this whole market at the global level would reach about 134 billion euros by 2030. And the biggest markets will be, are already now North America, Europe, and Asia. And the major application will most probably be about electricity production, internal use of the waste heat for production, and also district heating systems. So now, of course, now that we've seen the actual potential and see that, well, there are things to do, the question is, how are we going to recover this waste heat? So for those who are not in the field, how does it work? Well, basically we need, for at least for liquids and for gases, we need a piece of equipment called a heat exchanger, where we basically make the two fluids in contact. We have a hot fluid, typically the off gases, and a cold stream, typically fresh air that we want to preheat, or hot water or fresh water that we want to preheat. And in the heat exchanger, we are putting in contact the two streams via a system of tubes. So in the tubes here in this diagram, you see that we have the hot air, the hot stream circulating, and around these tubes, we have the cold stream that we want to heat up. So that means that the two streams are not mixed. They're still separated, but the heat transfer can occur over the bundle of pipes. So the most standard pieces of equipment for liquids and for gases are on the left side. You see actually this shell and tube bundle of a shell and tube heat exchanger. These are very often quite large pieces of equipment in industrial plants. We can also see the picture in the middle, plate heat exchangers, which are very useful because they can be very compact and very easy to dismantle for the maintenance. Or in certain cases, we can also deploy heat recovery steam generators, which are really major pieces of equipment. In this case, we circulate, for example, flue gases to cool down. And on the other side, we have fresh water being circulated within the steam generator so that the water can be heated up and evaporated, and if necessary, even superheated to, for example, be injected in a turbine. Solid streams, waste heat recovery is definitely something else. Here we have the big problem that there's not one-size-fits-all solutions. Shell and tube, plate heat exchanger are really standard pieces of equipment. In the industries, the know-how is there. But once we start talking about doing waste heat recovery from solid streams, it's really way more difficult. Why are we talking about this? Well, the thing is, it's solid streams are also a source of waste heat, and we should also try to recover it, of course. There are not yet values about this potential, but McBrien in 2016 did at least some estimation and stated that about 1/3 of steel plant, of the heating demand of a steel plant could be covered by standard waste heat recovery technologies, but this value could increase up to 44% if solid streams were included. This was a theoretical value. And as a side note, we at least are actually working exactly on this topic to see how could different technologies be deployed to recover waste heat from solid streams. Sorry. As an example, you see on the left side, the slag pouring. So slag is basically the residue that you obtain from steel melting. And this is basically, it's molten lava. Think about doing waste heat recovery from a controlled volcano. It's exactly this kind of problem. So here the question is, how could you do waste heat recovery from an initially liquid stream that is going to solidify once it's being cooled down? So once you start doing the heat recovery, actually your liquid is going to turn into stone, meaning that you can't use standard equipment. So to solve this problem, what is being done is basically the liquid slag is being poured down. Small droplets are created with this effect of dropping and also ejection of the slag. And with that, the area of the slag is becoming very large so that the heat transfer can be easily done. That's the first step of the treatment of the slag. What you then have is then a fluidized bed, which collects all these very hot droplets, slag droplets, and through this fluidized bed, you circulate air so that you can basically do the waste heat recovery between the droplets and air. So that's one specific solution. Another problem would be to do the waste heat recovery that you see on the steel beam on the right side. So here, of course, the question is, how could we recover the heat content of such piece? So here there are a few solutions. One solution would be to put these in some kind of tunnel that would use the heat radiation obtained from the beam to do heat, to do hot water or preferably steam, or to heat up thermal oil. That would also be possible. Another technology that is also that could be considered is to actually use this hot beam and put it in a container with having a sand-like material. And basically the heat would then transfer to the sand-like material. Once the beam is cooled down, we could take it out of the container and then come up with a new piece of a steel beam, which needs to be preheated before entering a furnace. And this preheating would then occur through the sand-like material that was heated up so that we have the heat transfer from the material to the steel beam. So that's a very specific solution for the steel industry, but that's also one technology to do solid stream heat recovery or heat transfer. So apart from this solid stream waste heat transfer, what are the main challenges to waste heat valorization? The first one is the optical heat exchange, the heat exchanger size. What you want to have, of course, is to have a right balance between CapEx and OpEx. You're investing in a heat exchanger to save your operating costs, to reduce your energy consumption, to reduce your CO2 emissions. But that means also investing in the heat exchanger. The bigger the heat exchanger, the more energy you can save, the higher temperature you can recover. Unfortunately, that means that the heat exchanger becomes, of course, more expensive. But if you do a too small heat exchanger, then the temperature level that you get out of it won't be very high. And that means that while you will have saved at the CapEx level, but you won't see much difference on the OpEx side by the waste heat recovery. So here in this case, it's really it's necessary to find the right balance to do a thermoeconomic optimization between the area of the heat exchanger, the size of the heat exchanger, and the cost related to that. Another issue also to take into account in practice is the space availability. We've had the case in some industries where the installation of a heat exchanger was partially constrained by the space available around. And that's also a very big topic when you're thinking about a heat recovery steam generator, because this can become a very large piece of equipment. The second challenge is the actual optimal valorization, because waste heat is not only about recovering it, it's also the question of once you have it, what do you do with it? And that's the challenge, because it's not necessarily just one solution, but you could make more out of it if you were to mix the valorization opportunities. Think about doing waste heat recovery from your off gases. You first produce electricity, you cool down the off gases, and then you keep the rest of the waste heat at a lower temperature, for example, to supply heat to district heating that is nearby. So that is one possibility. There are multiple configurations to take into account. Here as an example, we took the case, what you see is the south of Luxembourg with two steel plants. And the question that was raised was, okay, we do have waste heat. How shall we valorize it, considering that we have the possibility to produce electricity, that we have nearby district heating districts, at least, or that we have even industries that might be interested in using our waste heat. We developed a specific optimization problem for that. And as you can see, the biggest influence was actually the waste heat selling price that was asked by the steel plants. So if the price was low enough, basically the most interesting part, the most relevant solution was the production of electricity within the plant. But if the price became a bit too high, then the next solution would actually be to supply the waste heat to the districts around the steel plants. And of course, if the price was at the end too high, then nobody was interested in using the waste heat, and then nobody would then gain any use from that. So here it's really finding the right balance, taking into account the technical feasibility, but also the economic aspects of selling, buying the waste heat, the CapEx was involved and so on. So these involve quite a lot of variables to take into account that can be really challenging. Once you have waste heats, or at least once you have a heat exchanger, you really have to take into account maintenance. Maintenance is really central. Basically, and here I'm talking about giant tube and plate heat exchangers. Heat exchangers are not very complex pieces of equipment. They are quite static, but they require really maintenance, because if you don't look into that, you will have problems of fouling, meaning that over time you will have the formation of certain particles in the tubes, around the tubes, and the heat transfer efficiency will decline over time. And that's, we had also the case of certain industries installing heat exchangers, and after 3 years told us, well, you know what, we dropped it because it was not working. We were not seeing any difference. Yeah, but in that case, they were not really, they didn't look sufficiently into the maintenance of the equipment, into the cleaning of the equipment. You can have different kinds of fouling types. A big one is the corrosion, of course. If you can have the formation slowly of rust, which is going to decrease the heat transfer within the heat exchanger, and if you're unlucky over time, it can even destroy the equipment. Another possibility, of course, is the dust formation, so the sedimentation within the heat exchanger. So here in this case, it's really a problem of having solids being entrained within, for example, the flue gases. That's a standard problem that we have here. But here, that can over time clog up again the pipes. Another possibility is when you are having cooling water, or depending on the equipment that is connected with the heat exchanger, you can have biological activities. These biological activities very likely are going to produce some kind of slime, which is going to somehow insulate the pipes, and so that the heat transfer again is being reduced. And nasty side effect also of the biological activities is that over time the degradation can also actually lead to corrosion effect, because it can have some acidic effects. So that's also another problem. Scaling or crystallization, that's mostly the problem when you're having some forms of salt within your fluid. So the higher you go in terms of temperature, the lower the solubility will be. So the solubility will decrease over higher temperature. So that means that you will have slowly a coating within the pipes that is coming from these salts, again, clogging up the pipes. And then at the very end, and very specific, the organic decomposition or the polymerization of certain substances. With the decomposition, you can have the formation of coke or tar within your heat exchanger, or the polymerization, where you actually have the formation of different substances that are also going to block. So for these different kind of problems, there are always solutions. You can also, if you foreseen it beforehand, have cleaning equipment that can do the maintenance during the production, or if you don't have that piece of equipment, you then at some point need to stop the use of the heat exchanger, do the maintenance, and then reconnect it. In case of corrosion, you can avoid this kind of problem by using corrosion-resistant materials, but that means usually more high expenses. Biological activities, here you could use biocides, but here also this can also have a negative effect on the pipes if it's not well dosed. That's also tricky. The scaling problem, if you don't overdo it with the temperature level, that can also work, but yeah, it's really case by case. So this fouling effect is really central to really make it work, to really have a good waste heat valorization. So that was it. Thank you for your attention. We are working on this topic. And of course, we cannot help you with the maintenance, sorry for that, but we can help you on the optimization of your waste heat valorization. And you see in screenshots here, this is the heat to power tool. We are now working with ArcelorMittal on waste heat valorization on solid streams. That's the next step. So the conclusion is there is a potential there. We should use it also to address cost, OPEX reduction, but climate change also. And with that, we can definitely have also an impact. It won't solve everything, but it's part of the puzzle, and it should be taken into account. So thank you very much. And we'll see now with Maura what are comments and questions.
So how do you manage and optimize the temperature levels of waste heat recovery? What
we are using is process integration method. So basically, it's a method that has been developed more than 40 years ago, specifically for waste heat valorization. And what we do is we look at waste heat sources, so hot streams and streams that we want to heat up, cold streams. And what we're doing is then a match of hot and cold streams, but considering the different temperature intervals. So if we see that there is a hot stream and a cold stream in the same temperature interval, that means that in that interval, we can do a waste heat transfer. And by deploying this using mathematical programming, considering then technical constraint that this is a solution that we do not want to accept, then we can actually calculate and optimize the waste heat valorization of the system. So that's it was initially developed as a graphical method, but over 40 years, this approach has strongly evolved and it has become kind of a standard approach to this kind of problem, which is also applicable to water quality, actually, and also hydrogen production. So that's how we address this.
Okay, thanks for your answer. So we don't have any further questions for the moment. So on waste. Thank you very much.
Thank you very much, and then we'll be in touch then. Okay, bye-bye.
On waste.